Okay, only a few more chapters left, so we're at chapter 12, and we're talking today about inferences for population proportions. So, in here, we have to talk a little bit about the binomial distribution because a proportion is basically a yes or no question, similar to what we did back in when we were talking about binomially distributed random variables. So, that's exactly what we're doing here. So we have a two answer format. So yes or no, true or false, male, female, whatever we're looking at. We're looking at a binomial distribution. So our population proportion, so this is the proportion of yeses or successes or whatever you want to call it. We call them P or we can call it prop. That's our population proportion. Then we have a sample proportion. So that's denoted by P with a hat. I call it P hat. You'll hear me say that all the time. That's the success proportion for our sample. So basically we say X, which this X right here is actually, that would be our binomial X. The number of successes. Just like we did in binomial. And basically what we're doing is this P hat becomes kind of a scaled binomial because we just divide by n, the sample size. And so at this point, we now have our P hat, and this is what we're going to be dealing with. This is our sample proportion. So how many vehicles in Alaska are SUVs? A lot, actually. And we might want to make some sort of inference about the proportion of SUVs in Alaska versus the proportion of SUVs in the entire United States, for example. So this may be something that we might want to do with this. So, of course, every sample statistic, including p hat, has its own sampling distribution. So now, instead of talking about sample means, we're talking about sample proportions having their very own distribution. And the mean of our p hat is our true p, our population proportion. So this becomes almost normal, and here's skipping ahead a little bit. The central limit theorem, you can use a normal approximation of your binomial, and this can be p hat. So with the mean being p, and here's your standard deviation. The standard deviation of p hat, or the standard error of p hat, because remember, a standard deviation of a statistic, a sample statistic, is called the standard error. And this is what it looks like. P times 1 minus P divided by N. So now instead of N P times 1 minus P, remember, we scaled this down, so now it's divided by P. So, according to the central limit theorem, P hat will be approximately normal as long as we have sufficiently large N. Okay, forget what you know about 30. That was our rule of thumb for means, but when we're going to make inferences about proportion, we need to change that. It's no longer about the means. It depends on the P or the P hat, depending on if we have a P or not. And that's depending on if we do a confidence interval or a hypothesis test. So if our P or P hat is near 0.5, then remember, if this is close to 0.5, this will be very symmetrical. Near 0.5 means my binomial distribution is nearly symmetrical. So we don't have to worry quite as much of what n is. But if it's 0.01 or 0.99, Remember, if it's 0.01, that's way less than 0.5. That's going to be severely skewed right. This one's going to be severely skewed left. So we have a bit of a problem because we have to have a large enough n to pull this over to being normal. So here's a rule of thumb. Both of these have to be true. The n times p, and that's the hypothesized p, right, has to be greater than or equal to 5, or if we don't have a hypothesized p, then np hat is greater than or equal to 5, and n times 1 minus p has to be greater than or equal to 5. Or again, if we don't have a hypothesized p, then n times 1 minus p hat is greater than or equal to 5. So basically, these over here, you can also say the x, so the number of successes has to be more than 5, and the number of failures has to be more than 5. So how do we set up these tests? So let's start with the one proportion z-test. So your null hypothesis, again, always equal. Oops, I'm going to write actually. Always equal. So remember, null, again, is like that. So I said you could either use P or prop. One of the reasons that I like to use prop is because your calculator uses prop, because you don't want to confuse this P with your P value. Those are completely different things. So now your alternative hypothesis can be less than, greater than, or not equal to, left-tailed, right-tailed, or two-tailed. So your test statistic goes back to a standard normal. So we're not using T, we're back to using Z. And we just do our standardized form. P hat minus P naught, because remember, P naught is our hypothesized mean, divided by the standard deviation, which is the square root of P naught times 1 minus P naught divided by n. We would then calculate your p-value according to standard normal. So you would use normal CDF to find out your p-value using this number, and you would make your decision and your conclusion. Okay. So let's talk about how we do this using the calculator. So we have these assumptions. SRS, if you can't remember what that is, that's simple random sample, because you have to multiply by something else if you don't have a simple random sample. The n times p naught and n times 1 minus p naught are both more than 5, or at least 5. So always, you guys know, I've said this 1,000 times, write down your null and alternative first. So here's what you do. You're going to go to stat, tests, and then 5 is one prop z test. P naught, that was where you put your hypothesized proportion, the number that you think the true population proportion is and want to prove that it is less, more, or equal to. You put in your number of successes, you put in your sample size, and you highlight the appropriate type of test. So then you calculate. All right, so let's do an example of this on the next page. All right. Oh, there's the output. I'm sorry, the page is, let me go to the next page and we'll do the example. So we want to know if Alaska Native students are represented at UAA at the same percentage of the Alaska Natives in the state. According to the census data, 15.6% of Alaskans identify as Alaska Native. A sample of 245 UAA students found that 31 of them identified as Alaska Native. Do the data indicate a difference in the proportion of UAA students who are Alaska Native versus all of Alaska? So step 1 is always to set up our null and alternative hypotheses. So the question being asked, a difference in the proportion. So the question being asked is the proportion, and you can even put a little UAA here, is the proportion at UAA different from the all of Alaska, which is, and I'm going to write this as a decimal, not as a percent, because your calculator will not allow you to put that in. Or is the proportion at UAA still the same as the Alaska state proportion? So we start by doing that. So let's go to our calculator, and we're going to go to distributions. Oh, no, we're not. I'm sorry. Forget that. We're going to go, whoops, I keep thinking. Okay. Get off of there. We're going to stat, tests, and number 5, which is 1 prop z test. All right. So my P naught, that's my hypothesized proportion. So that's right here, 0.156. Whoops. The 1 didn't get in there. X, this is how many successes. So X, number of successes. And so how many Alaska Native students did I have? X equals, I had 31. And then N, how many did I poll? 245. And then notice it says prop here. So do I want a two-tailed test? Yes, I do. Enter and calculate. And so here's my output. The first thing it always gives me, just like everything else, is it always likes to give me rewrites your alternative hypothesis. Is this the alternative I had? Yes, it is. And it gives me Z, which is negative 1.27. So I always want to report my test statistic. Because remember what that tells me. That's how many standard deviations away from the mean I am. So this is 1.27 standard deviations away from the mean. And it's giving me a p-value of 0.204. So this is my p-value. And it says p, I like to write PV just so I don't get all the p's mixed up. It also reports my p-hat, which is nice. And that was basically equal to 31 over 245. So this was my sample proportion. In my sample of UAA students, 12.6% were Alaska Native. And that is different. It is different than what the census data says that Alaska as a whole is 15.6%. However, p-hat only gave me 0.126. Now that's 3% different, but is that statistically significantly different? Well, we have a p-value of 0.2, so what would we do? You should be saying to your computer right now, do not reject. We do not have sufficient evidence to conclude a difference in proportion of Alaska Native students at UAA versus the 15.6% Native Alaskan population. In the state, I guess is a good way to say that. Okay. So, we do not have enough evidence. We do not have sufficient evidence to conclude a difference in proportion of Alaska Native students at UAA versus our 15.6 Native Alaskan population in the state. So, what they're saying is that 12.6%, that difference could occur just by chance, that 3% difference, simply because, weird things happening. So, I want to make sure, did we violate any assumptions here? Remember that N times P naught, this is our P naught, has to be more than 5. Would 15% of 245 be more than 5? Yeah, definitely. I don't even have to figure that out to know that. So I'm not too concerned about it. And I know, of course, the opposite will be. So 85% or 84% will definitely be more than 5 as well. So I don't have to worry about that there. Okay, so now let's move on to the confidence interval. If we want to find a confidence interval for the true proportion, then our formula looks just like this. Now notice we're a little bit different here. We go p hat plus or minus the z at alpha over 2. Remember, this is the z equaling, it's either going to be 1.645, 1.96, or 2.576, depending on if I have a 90, a 95, or a 99% confidence interval. Okay, so that's what the z is going to be. And now look, I don't have a p naught, so I have to just use p hat in there. So it is going to be a little bit different. And when we do our assumptions, of course, we just have to make sure that x and n minus x are both greater than 5. Okay, so let's use our calculator to do this as well. Now, again, our assumptions, we go to 1 prop zint. This is very simple. You just put in the number of successes, the sample size, the confidence level, and hit calculate, and you're ready to go. Okay, and the output is just going to give you your confidence interval, your p hat, and your n. So, what is the 95% confidence interval for the proportion of students at UAA who are Native Alaskan? So, let's remind ourselves really quick. We had x was 31, n was 245, and that's really all we have and all we need. And then our C level, of course, is 95%. So let's go over here. We go, I keep wanting to go to distributions for some reason. I think I'm used to it. Okay, so we go here. Now we want to go down to the interval. So you have to make sure it says interval. 1 prop z int. So it's a 1 prop z int. And what's really nice about those of you who have the 84s is it actually keeps in just the last thing that you did, even if it was a 1 prop z test. And so you have x is 31, n is 245, your C level is 95. So you're going to hit calculate, and you find out that 0.0849 to 0.16816, and we are, and you can say it like this also, the way that I've been writing them in class also, is our P is between these 2 points. So we are 95% confident the true, and make sure you write the word proportion of Alaska Native students at UAA is between, and you can even turn these into a percentage now, 8.49% and 16.82%. Now you'll notice that this also gives me the same conclusion that I drew in my test, because remember, the state of Alaska is 15.6% native. Is 15.6% contained in this interval? Yes. So it is possible that the UAA students are 15.6% native, because that's within our 95% confidence interval. And you'll also notice it gave you the p hat and it gave you the n as well. 0.127, yeah. And n was 245. Okay, so let's move on to the next thing we want to talk about. If it'll move on me, and it won't right now. Okay, got it to work. Magic of the pause button. So, remember, margin of error, I like to call that ME anyway, is Z times P hat, 1 minus P hat over N, with a square root. And so it's also half the length of your confidence interval. Remember, you can take your upper bound minus your lower bound, then divide by 2. So you can actually find your margin of error that way. So if we are given, so now let's say that we are given a needed margin of error, and we need to find a sample size. I said it. We need to find a sample size. Now rearranging this thing gives me this guy right here. N equals, excuse me, P hat times 1 minus P hat times, or Z over E, and all of that squared. However, if we haven't taken the sample yet, I don't have a sample proportion, so I don't have a P hat. So I go, wait a minute, I don't even have a P hat, so how am I supposed to figure out an N? Well, one of the things we can do is we can figure out, well, what is the highest number that P times 1 minus P can actually be? And here's getting into just a bit of algebra, but if we have P minus P squared, that's what P times 1 minus P is. I just distributed the P. If I graph this, it's going to be a parabola, right? P times 1 minus P. And it's a parabola that's going from 0 to 1. Because P is always less than 1, right? So this is the only places it's going to go. P has to be between 0 and 1, so this is the only place P is going to go. This is P, and then this is P minus P squared on the y-axis. Now look at this. This maxes out at 0.5. But what value is this at 0.5? Well, 0.5 times 1 minus 0.5 is 0.5 times 0.5, which is 0.25. So the highest that this number can ever be is 0.25. That's that maxes out there. Because if I'm over here at 0.4, well, 0.4 times 0.6 is 0.24. That's right here. If I'm at 0.3, 0.3 times 0.7 is 0.21. You see what I mean? It goes up. But then if I'm at 0.6, it's 0.6 times 0.4 again. So it's going back down. So the highest it can be is 0.25. So when we don't know anything about P, we're just going to call P times 1 minus P 0.25. And of course, you have to round up again. But this will give me the sample size needed for a margin of error of at most E. Now, it may be smaller. I may get an even better margin of error if my number is not that high. So, back to our example. I want to estimate the proportion of UA students who are native with a margin of error of at most 3 percentage points. What sample do I need? So I'm going to not assume anything about P. Now, if I want to assume something about P, if I assume that P, the highest P can be is 0.3, then I wouldn't use 0.25, but I'm not going to assume anything about P. So my N is 0.25 times Z over E squared. And I didn't say what I wanted, so I'm going to assume that I still want a 95% confidence interval. And the E that I want is 3. So n is equal to 0.25 times, and my z with the 95% is, you should be saying 1.96, I hope, over 3 squared. So I'm going to go 1.96 divided by 3, square that number, and then multiply by 0.25. Oh, that didn't work, did it? Did I do it right? Oh, 3 percentage points. Terry, I should have done that right. 0.03. Okay, that works. 3 percentage points, which is 0.03, right? I see what I did now. 1.96, let's do this right this time, divided by 0.03 equals, ooh, big number. Square that, multiply by 0.25, that'll get a little better. And the answer is 1067.1. Round that up to 1068. So I inadvertently, I did that on purpose, right? I'm not going to retape this, so. But I'm going to keep it because I think I just showed you guys a really good way not to make the mistake. Because if it says 3 percentage points, remember that means my error is actually 0.03. So it's really important that you guys do that. And again, even though this is 0.1, you still have to round up. So it's actually 1,068 students that I would have to poll in order to get this small of an error, margin of error. All right, let's move to the next one. So this one is actually for the next section. So that's all there is for today. And I will start on the next one. So all we have to do is a 1 prop z test and 1 prop z interval for this next worksheet.